The subject for today's sort of workshop or presentation is this introduction to quantum protocols. Normally, a lot of people will go down the rabbit hole of algorithms, and algorithms are very powerful, but protocols are also another important thing or application of quantum computing that I argue are equally as important. And I'll make clear what the distinction is as we keep going on. So here are the objectives for today's meeting, just stuff I think a high-level overview of what we'll be covering today, and it's stuff that I'd like to cover within the time that I have here. So we're just going to sort of recap the last meeting and address some continuity. So what are we doing from the previous meeting and bridging that to today's meeting. As I promised just a couple seconds ago, we're going to make that distinction between algorithms versus protocols. I feel that's crucial to understanding the difference between quantum computation and sort of quantum information, which are very intimately related, but should still have a degree of distinction between them. And then we get to DiVincenzo's criteria. This is something that doesn't get brought up a lot with a lot of sort of introductory quantum computing courses, but I always like to bring it up because it's sort of the big picture goal that we're shooting for here in the realm of quantum computing. And finally, I'll sort of touch up on quantum teleportation and try and give an intuition as to how one would come up with that protocol. Like, what is the motivation for teleportation, and how one could go about sort of deriving it. Keep in mind, this is introduction to protocols, so you will not see too much math just yet. For math, I always direct people to our GitHub, which has the workshops that I've already detailed a lot of the math. And then it's very possible that in our next meeting, I'll actually walk you through the actual Dirac sort of Brocket notation, the matrices, and then you can actually see for yourself, okay, here's how the numbers sort of add up. All right, so last time, let's see, we went through the properties that quantum computers use. And these are properties that are sort of shared amongst all quantum computers. So I made a very clear distinction last time about the difference between sort of universal models of computation, like the gate model that IBM Q uses, versus quantum accelerators or co-processors, like what Xanadu has with their optical-based system, or what D-Wave does, which is still a superconducting qubit system, but which uses a very specific problem which they target, which is quantum annealing, or AQC, adiabatic quantum computation. And the three properties that all of these things have are superposition, entanglement, and the no cloning theorem. And it's kind of weird seeing the no cloning theorem as a property that's used, but I put it there because it's an inevitable consequence of dealing in the quantum realm. It's something that you have to exercise a lot of caution with. So once again, just a brief reminder, superposition is just this idea that given some quantum system, it can be in a kind of unknown state. And then when you make some observation, if you have to interact with the quantum system to make the observation, it collapses into some well-known state. But when you have not made the observation yet, and it might be in this, there's sort of like a probability distribution of what it may be until you officially make the observation. Entanglement is this idea that I try to do the best to not go into too much quantum mechanical depth here, but it's the idea that we can have a quantum system that may be physically separated, but they may share their inherent quantum property. So if I manipulate a qubit from one physical location, the other one will have some instantaneous change in its state, and it's highly correlated behavior. And the focus of this presentation, you will see this, I'll go into a lot more depth over entanglement. The reason being is it's a very powerful concept, but it's only powerful if you understand it properly. So I think it's well worth sort of diving deeper into here. And as I mentioned earlier, universal versus non-universal methods. So IBM and Rigetti both have their own sort of gate-based models with superconducting qubits. And then we have other companies with their sort of what Xanadu is doing with optical, and D-Wave with sort of annealing. And we also went over some current applications. So finance, optimization problems. D-Wave is betting heavily on that, although the research is still highly controversial at this point. And especially in the realm of material simulation, quantum computing has been garnering a great deal of attention. All right, so now we can actually get into the content of today's material. And I want to start off at a very high level of what it means, the definition or difference, between an algorithm versus a protocol. So the way I always like to think of this is that a protocol always defines how a system should work. And the examples that I give are, network protocols, TCP/IP is like one kind of network protocol, or how a car operates. So if I give you some system and then I tell you this system is X, that system should provide all the properties that any system labeled X should have. It's the essential, the protocol is just literally how the thing should operate. So what is permissible versus what is not permissible. It's a very structured layout for it. For example, with the network protocol, if all the computers understand a certain protocol, that's great, because if I write an application for one computer that uses a network protocol, and if the other computer can understand the network protocol, we have a standardized way of communication. That's all it is. We just defined how the network system should work. Now, an algorithm takes a sort of a distinction from protocol, where an algorithm is a little narrower in what it does, but it's just a set of steps to help solve a certain problem. So the protocol doesn't tell you how to solve something. It just tells you how something should work. But the algorithm might be built on top of a protocol. An algorithm can very well use a protocol to achieve its goal or the problem it's trying to solve. So Grover's algorithm gets brought up a lot in quantum computing, mainly because it's sort of the poster child of the things we can accomplish with this technology. It's the ability to sort of perform a search on unordered data in a big O square root of n time. And all that really means is, if I'm given some unordered data, like, for example, I might have a pile of paper, and, normally for humans to sort through unsorted data, we have to look through every single piece of paper and make a distinction about oh, is this what I want? Nope. I'll move to the next one. Is this what I want? Nope. And we keep going through that. What's sort of extraordinary about Grover's algorithm is we're saying that we don't actually have to go through every n items. So for any the best case search algorithm, big O of n. But to be able to do sub n time is an incredibly extraordinary feat, and it's something that's garnering just a lot of attention. And bubble sort. Bubble sort is sort of the brunt in terms of the sorting algorithm litter, because it is an example of a sorting algorithm. It's very easy to perform mathematical analysis on it, but it's pretty bad. It's used in the real world for only very limited specifications. But I digress. These are just examples of protocols, and then we have examples of algorithms. And now we want to sort of put it all together. So protocol, as I mentioned earlier, can define a system you can use, where an algorithm can define how to solve a problem with that system. And one of the examples I can think of is if you have an automobile, right? A protocol might define how the automobile works. So if I put my foot on the gas pedal, the car should go forward. If I hit the brakes, it'll stop. But there might be an algorithm for me to get to Taco Bell. I mean, it's a set of directions. And for anyone who's studied computer science, this picture should be somewhat familiar. It's Dijkstra's algorithm. It is a graph-based algorithm, and just an example of how the protocol may define how you create the network and what properties a network should have, or graph. But the algorithm will tell you how to do something useful with that, with said graph. So. Okay, now we can sort of get into what DiVincenzo's criteria really are. And I kind of did this hand-wavy thing where I said, oh, it's the big picture of what quantum computing should be. Well, the reality is it's a number of criteria that any universal quantum computer should meet. So it's stuff that any user of a quantum computer, or anyone doing something useful with the computer, should seek out in a real system that they want to call a computer. So the main criteria focus on the idea of computing itself. So, these are just some highlights. It's got to have gates, it's got to have long relevant decoherence times, and we need to initialize the qubits into a well-known state. Just to give you guys a better idea of what that is, there's a whole section dedicated to the criteria here. But you see the main criteria here. So there's sort of 5 bullet points, and I've highlighted sort of 3 of them. And then there are 2 other ones that we'll really delve into, because our focus of today's meeting is quantum protocols, and these are definitely a key component of that. So, a scalable physical system with a well-characterized qubit. So what does that mean? Well, what that really means is that we want some system. Yeah, let me see if I can. Okay, awesome. Now you guys can see my sort of unofficial whiteboard here. And the idea with the first point, a scalable physical system and a well-characterized qubit. So a scalable system means that I can keep sort of adding qubits to my system. And the cost of adding each qubit should be linear. And what do I mean by cost? I mean the way the resource usage grows. So, if I put this as the number of qubits, I just put, hashtag Q here, and then I put the sort of cost for it. So maybe the amount of power, the amount of hardware, we would very much like it to scale linearly. A good system will allow me to sort of add these qubits, and the cost will just grow in this kind of fashion. And superconducting qubits do have that advantage, that it doesn't penalize you too much to keep adding qubits. I mean, you have to worry about refrigeration and power consumption, but those are trivial matters. Optical computing, though, this is a problem that a lot of optical-based platforms have, is that the cost of adding another photonic qubit kind of grows exponentially, which is highly undesirable. This cost for, this is for sort of optical systems, and it just grows exponentially. So you see right off the bat, optical computers don't really seem to, oh, we got something in the chat. I think there were problems with wiring. Oh, yes. Okay, so Amir brings up a phenomenal point here, is that there are problems with wiring for superconducting qubits. And he's absolutely right. Because I think, I don't think DiVincenzo's criteria mention anything too much about entanglement, like the criteria for entanglement, although I can see it becoming a problem very quickly. And what Amir brings up is that in superconducting qubits, so you got to remember that those qubits live on this kind of planar circuit board. It's a 2D surface, and we really want to use entanglement. Like if I have a qubit here and a qubit here, it's not too hard to sort of set up the hardware to entangle these two qubits. I mean, they're physically on silicon here. But if I have a system where I need a lot of entanglement, I can't physically, sort of bring this qubit closer. I'll have to find a way to sort of wire it together. And the further the distance, the harder it is, and the more qubits you have, it becomes just this total mess to kind of wire things together. Rigetti, I remember when our school did have we did have an engineer from Rigetti give this awesome presentation, and that's something that they've been tackling as well. I mean, their architecture has this kind of octagonal pattern with their qubits, and one of the chief complaints that the researchers have is that there's not enough entanglement happening. So that criteria doesn't get covered explicitly by DiVincenzo. And just to give some context, DiVincenzo was, he's a physicist. He came up with this criteria in 2000. And there's no explicit statement of how much entanglement we want, but it should be there. I mean, as I mentioned before, like the three main properties that a quantum computing system should exhibit are the ability for superposition, for entanglement, and the consequence of those two is the no cloning theorem. So that's something that, that's an excellent question, and I do appreciate you bringing that up. But, once again, sort of going back to that point, a well-characterized qubit and the scalable physical system. Well-characterized, what that means is that the Hamiltonian of that qubit should be well-defined. What is the Hamiltonian for those of us that aren't, too ingrained with physics? So the Hamiltonian describes the energy of a certain configuration. And usually, the Hamiltonian is equal to the kinetic energy plus the potential energy, Ke plus Pe. And we want this Hamiltonian to have a very very solid definition, because if we're manipulating some kind of qubit or some quantum state, we need to know, okay, how much energy do I have to add to get to a certain desired state, so on and so forth. And, if you're really into quantum mechanics, the actual, for a lot of superconducting qubits, your potential becomes this, it's a well potential. It's a very well-defined well potential. And then you have like your sort of standing waves, and you could go through the whole classical process if you wanted to. But for the sake of this workshop, as introductory as it is, I have decided to refrain from going to such extent. And then we want to, okay, then there's this other point here, initialize the state of qubits to a simple fiducial state. So, so prior to executing the computation, the qubits should be in a well-defined state. So what this means is, classically, when I put a program through a computer, the data is already sort of in a good configuration. What do I'll tell my computer, I want you to do 2 + 2. Internally, the computer is going to see, okay, so this is the bits 1 and 0, and these are the bits 1 and 0, and 1 and 0 are incredibly well defined. So for a classical computers like the one that you're watching this sort of Zoom meeting on, everything is very well defined. For qubits, it's a little trickier. I mean, we're dealing with the quantum system here, but the idea is, okay, like I should be able to start off my computation in either like maybe the one state, or I should start off in the zero state, or if you're using IBM Qiskit and I think a lot of other simulators, they will let you perform some kind of arbitrary initialization. So I might have some weird, I could have it in a Bell state, right? It could be a plus or a minus. And if you don't know what these symbols are, don't worry. I do have some workshops planned for that stuff as well that are a lot more math heavy, but this is just sort of conceptual, is that I can set the configuration up properly. Otherwise, it makes no sense. Like, why would I have a computer that does not let me set up my data properly prior to computation? So imagine like if you had your calculator and you said 2 plus 2, and the computer said, oh, so you mean like 2 plus 100. That's a fairly useless system. As cool as the quantum part may be, it's still useless if I can't put in the information properly. And we want long, relevant decoherence times. So I mentioned this rather briefly in our last meeting. And okay, the idea behind decoherence times is the fact that for most superconducting qubits, we have this problem where I might set up something in a very well-defined state, like a qubit. And over time, just because of interference from, background interference, or maybe poor quality gates, or maybe I perform too many manipulations, the qubit will kind of lose its quantum nature. It sort of devolves into a classical system, which introduces error into our computation. So for superconducting qubits, lifespan is not something they're very well known for. They usually decay fairly. I mean, we can do computations quickly. So if you either have to find a way to do faster computations in that limited amount of time, or we can seek to have sort of longer living qubits. And I think the longest lived qubit is not a superconducting qubit, but it's based off an ion trap system. So if you're interested, you can check that out. I think the longest time they've managed to have it live is like 30 minutes in a superposition state, which is impressive. But the problem with ion traps is they fail that sort of first criteria, which is being scalable. They also suffer from this kind of exponential cost as you keep adding qubits to your system. We want a sort of universal set of quantum gates. So that just means that there are a number of manipulations that I can apply to this qubit. And you might be already familiar with, like, a Hadamard gate, or, I can put it through like a Hadamard, or I can put it through some kind of C0 here with yet another qubit that might be in some other configuration. And there should be a universal set of these. And the example that I came up with, there's a very nice classical analog, is the NOR gate in normal computing, normal classical computing. The NOR gate can be connected and rewired in a number of ways to derive any other gate that you're interested in. IBM has a sort of similar method with their Qiskit platform. They do have a kind of a universal unitary gate. And the idea behind that gate is you can put your qubit into any sort of arbitrary desired position, or you can wire those gates together to create another gate that you're interested in. So if you want to create a custom gate that's not offered, no worries. They have this kind of gate. And if you're more mathematically inclined, there's a theorem called Solovay-Kitaev. I think it's the Solovay-Kitaev theorem, which states that given a limited set of gates, you can actually do a pretty good job of approximating any arbitrary quantum state that you want. So this is highly desirable in any quantum computer. Now, okay, see, I mentioned it here, the Solovay-Kitaev theorem. Now, the problem is, we're already you see that there's no system in existence right now that satisfies all of these criteria. D-Wave falls apart when you talk about this, because D-Wave does not have a set of gates. It doesn't even use gates. It uses biases and couplers for their adiabatic method of computation. So this already falls apart. Whereas, Rigetti and IBM are like, okay, we've got gates. We can, perform all sorts of neat sort of quantum computations with them. Qubit specific measurement capability. So this is just your ability to sort of extract a final state, like the quantum state will collapse into something, and you should be able to see something. Okay, now we sort of get into what quantum teleportation is all about. And this criteria wasn't added until I think a year or two later after DiVincenzo's original criteria. And this was brought up because, sooner or later with all the quantum computers we have, we want the ability to kind of transmit information between quantum computers. So maybe in the very far future or very close future, depending on how R&D goes, we'll have this kind of quantum internet. We'll have quantum channels. We can funnel quantum data through it, because the problem is, without that ability, I have to convert my quantum state into a bunch of classical data. And you know, the limitation with simulating, you know, quantum states on a classical computer becomes incredibly prohibitive. Last time I mentioned the NISQ era. Once we get to like the 50 qubit hotspot, you're on your own. Like even the best supercomputer in existence cannot simulate more than 50 qubits. That becomes sort of the ceiling that we have to be able to work with. So this ability to interconvert between stationary and flying, once again, I argue poor terminology, but a stationary qubit is something that sort of remains in your computer, whereas a flying qubit is one that gets transmitted back and forth between quantum computers. So it's something that, it's the actual messenger, and the stationary qubits are the one inside the computer. So now I'm going to try and sort of bring the intuition for quantum teleportation. You know, what is it, and why should I even bother with it? And all right, so we'll start with the problem. And our objective here is that, we want to send a quantum state to some other party. So this is the part of like having the quantum internet and quantum channels. We want this ability to have data on a qubit and send that quantum data to another quantum system. We don't want to collapse that quantum data or have to, perform all sorts of measurements and in the end sort of down convert our quantum data to classical data, because there are just limitations on the capacity of having to store that quantum state, and so on and so forth. So here are a number of thoughts that I think you could someone could naturally come up with the information that I've sort of presented from our prior workshop, and especially for members who have been with the organization for a little longer. So we could find some operation that copies the state of our qubit to their qubit, right? Like if I have two parties, I should be able to I don't know, I'll just take one qubit. We find some imaginary unitary gate, and I shove that qubit in, and then the other qubit will be like, okay, now there are two qubits that have the same information. And this should be a very nice property to have. Unfortunately, we can't do that. This is the reason why I'm so sort of hell-bent on reminding people, like, the no cloning theorem is a thing. You have to be aware of this, and this is a major rut in terms of thinking. Like, if superposition and entanglement somehow you have the ability to understand easily, no cloning will always bite you in the butt if you're not careful. So the no cloning theorem forbids anyone from copying an unknown quantum state. So what I mean by that is if our qubit is in some superposition, like I have a Bell state, so it's kind of floating in that realm between the ket 1 and ket 0, I can't copy that because the inherent act of copying means I have to disturb the quantum system, and in the end I lose the data anyway. And there's a post, I didn't put in the slide unfortunately, but it was written by IBM, and it's a very, very elegant mathematical derivation. It's not too intensive, but it does require you to understand a lot of the Dirac-Brocket notation and some of the existing terminology. But it's still a very nice derivation that shows you why the math of quantum mechanics forbids such a thing from happening. So, okay, let's try thought two. So if I can't copy things, maybe I can entangle them. Like maybe I can sort of tie a string to this qubit and link it to another qubit. So if I perform some manipulation, the other party, upon receiving that entangled qubit, can sort of see what I'm doing, and they'll be like, aha, now I can sort of get the information of what that unknown quantum state may be. So in the process of doing that, I might destroy the original qubit, but the other qubit still has the information. I've teleported the information over. So, but then you see that I've got this nice little picture here, friendly little illustration. Yes, but not really. You got to put a little more elbow grease into these things. If any physicist, mathematician can tell you that nature is not always keen to reveal its secrets and methods as willingly as we would like it to. So as I mentioned, little extra elbow grease required. So we can teleport an unknown quantum state, but we can't copy it. And that's where the teleportation, or why we call it quantum teleportation, we're teleporting information. And I want to emphasize that because I've had people before who think teleportation is like, it's like something from Star Trek where, beam me up, Scotty. And they got the, they got the little thing they stand on and they're physically teleported to another location. This is not what happens in the context of quantum computing. The reality is we're just moving information from one place to another. So we essentially circumvent the barrier that the no cloning theorem creates. But in order to do that, we have to kind of hybridize some classical and quantum operations. So what this means is that we can't just like sort of jiggle the entangled qubit, and then the other party will see the jiggle, which they will, and then they'll know exactly what state it's in. Not necessarily, and this has to do with the limitation of entanglement, which I'll go over after this slide. So in order to perform like the smallest example of quantum teleportation, we're going to need 3 qubits. So we're going to need 2 entangled qubits. Qiskit, their example has this kind of like cuddly third party that's willing to do the entanglement for you, and then spread the 2 qubits between you, Bob, and the receiver, Alice. Fun fact: the whole terminology between Bob and Alice is very traditional cryptography speak. Bob's always the transmitter, Alice is the receiver, and the malicious eavesdropper is Eve. So that's why they call them Bob and Alice. So the solution here is we're going to use the entangled qubit to transmit what we can, and then we have to use classical bits to make up the state by knowing which operations to apply. So that might sound like I'm being hand-wavy again, and you're right. I'm intentionally being hand-wavy to just try and give you the big picture, and we'll kind of sort of narrow it down. So, whoops, I've definitely jumped the gun here. So I'm going to go back to my handy-dandy whiteboard here. All right, so the idea behind the whole thing with teleportation, or the cautionary tale that I want to give with entanglement, is there's kind of this misconception that, okay, let's say that this is Earth, and then this is me. Woohoo! Go anthropomorphism. And I've got some qubit here, and I'll just say it's got some kind of 0 state, and there's someone far away in space. They're just very far away from me. And they also have the qubit. Somehow we figured out how to sort of do the teleportation process, and they also have the qubit. And they're entangled. They're highly correlated. So what this means is I can sort of, I can perform a manipulation on this qubit. Like maybe I'll turn this qubit into a 1, and then they might see something like this qubit should also, go into another state. But the problem here is it's not always guaranteed that this qubit will become a 1, because entanglement just means highly correlated. It doesn't necessarily mean perfectly correlated. So it doesn't mean that like, I have like a kind of cheat table here that will tell me, okay, if I'm in 1, that qubit must be a 1, and if I'm in 0, the qubit will also sort of turn to 0. That's not true. It could very well happen that by just by the nature of the system and the uncertainty, that I could have my qubit in the plus sort of Bell state, and the other qubit will be like, oh, I am also, I might choose to be in minus, or I might choose to be in plus. So with that limitation, I have to send some classical information, like a kind of heads up, a pat in the back that says, hey, if I send you a 1, it's going to be this. If I send you a 0. So you're going to need to send some kind of classical information to your other party to let them know, like, okay, the qubit, the state that you got from the entanglement, you'll now need to perform a little extra manipulation, a little more elbow grease to get to the subsequent state, which will then be the true superposition that you want. So in the process of doing teleportation, the state or the unknown qubit gets destroyed, but the qubit on the other end receives it. On the Qiskit platform, the IBM Q platform, you will be able to, what they'll do is you do the teleportation on a single computer. Unfortunately, they they have yet to build support in for like actual long distance sort of physical communication, but that's something they'll probably be approaching in the near future. And there are other protocols as well. So what I gave is sort of like a rudimentary building block for what you might see in other qubits too. So BB84 is one of them, but then you see like there's a whole slew of these protocols, and you'll notice right off the bat, like they all have these very long sort of alphanumeric acronyms for them. But one of the also other things that I didn't mention is that for this protocol, I didn't tell you the nature of the hardware. So in an ideal universe, where we have quantum computing and it's at where we want it to be, the hardware shouldn't matter. Like all quantum computers should be able to support the same kind of capabilities. But for the case where we are now, superconducting qubits are terrible when it comes, like we can't really do that kind of idea where I can physically move a qubit. We're not there yet. But all these protocols assume that you're using a light-based quantum system. So you're using some kind of optical quantum computing. And that's one of the benefits of having photons. You're using photons as part of your quantum computing system, because photons don't decohere very easily, and they're transmittable, which means like I can have my quantum computer in one location, and then I can shoot some kind of laser, and I can use those photons in different physical locations. The problem, though, is that the strength of photonic quantum computing is the same as its weakness, and it's that photons don't really interact with stuff all too well. They're not, they're not like actual other particles like protons or electrons that are, more than willing to, once they make contact with another particle, though there's some instantaneous kind of reaction to it. And there's a way to sort of, use microwave pulses for superconducting qubits. There's just a nice way to interact with them. With photonic computing, it's a lot more nuanced, and you got to use all kinds of fancy optical equipment like beam splitters and whatnot. And that sort of goes full circle back to what I said earlier with the fact that we want a scalable system, and we don't want an exponential growth in hardware cost when we're just adding qubits linearly. So that's one of our that is one of the concerns here. And for now, just for now, all the protocols, all the real research and protocol development is focused on quantum key distribution. So what is it meant by, let's remove the quantum part. So whenever you're learning anything in quantum computing, just remove the quantum part. And there's usually some kind of nice classical analog that you can look at first before you make the mental switch over. So I just cover up quantum and we just look up key distribution. So the idea behind key distribution is there should be some kind of, there might be two parties that want to communicate with each other. And in a lot of existing cryptographic encryption schemes, it requires that each party has a kind of private key, and we can use this key to encrypt our messages and sign everything. But ideally, we want a way to kind of distribute, keys securely, or to generate and distribute securely. So one of those ways is we can exploit quantum mechanics to do that, to both generate the key and to kind of get it out properly. BB84 is like the simplest example I can think of, but it's all of these protocols use some method of photonic qubits. So the terminology might be confusing because whereas, in sort of what IBM and Rigetti do with their superconducting qubits, in optical systems, they're like, polarization. You've got to worry about photon polarization. You have to worry about, I think, because Xanadu does sort of this Gaussian boson sampling, GBS, they always refer to some kind of Hamiltonian and squeezing, photon squeezing. That's what they call it. So something to be aware of. All right, so I think that's the end of what I had in store for this sort of introduction to quantum protocols. Once again, I intentionally refrained from showing too much of the heavier math, so much as just giving a nice sort of fundamental understanding. Like, what is the difference between an algorithm and a protocol? And as I mentioned with today's objectives, here we go. We did manage to go over the criteria and get a sneak peek of like teleportation and the intuition behind it. So I want to do this, but I need to do this in a quantum context. So I got to use my quantum toolkit, like entanglement and superposition. And how do we sort of work within that toolkit to produce a viable result or a viable system?